Hello, this is Dr. Divya Pradhan, and today we are going to talk about Hardy-Weinberg equilibrium. Alright, so Hardy-Weinberg equilibrium is also called genetic equilibrium. Why? Because a population in which the allele frequencies do not change over time is called Hardy-Weinberg constant, Hardy-Weinberg equilibrium, or Hardy-Weinberg state. It is a stable, non-evolving state. So let's see what he's talking about. Let's see what allele is. Allele is the version of the gene. So for one gene, there can be two versions, right? From the mother or the father. Better still, let me explain. Here is a chromosome, and I can talk about a chromosome, say for example, chromosome 20, and I'm talking about a loci in this chromosome 20 of one individual. And let's talk about a gene, and we can say it is X1. So what am I saying? I'm saying the number of this gene in this particular loci of chromosome 20 of all the individuals in the population, whatever number it is, you can say 20,000, 30,000, 40,000, 50,000, the number of this gene will remain constant. That's what I'm trying to say. As long as there are some conditions. As long, and we'll talk about conditions later, okay? So what he said was, what Hardy-Weinberg said was P plus Q equals to 1, where Q is the recessive allele and P is the dominant allele. So therefore it follows P plus Q times P plus Q will equals to 1 times 1. You agree? So 1 times 1 is 1, and P plus Q times P plus Q is what? P squared plus 2PQ plus Q squared. This is allele frequency. This is genotypic frequency. Either way, it is constant. This is a genotype, remember. This is an allele. Clear? Alright, here I just lifted something from your textbook. You are going to use this for the lab. It is showing a population of 25 moth and total 50 alleles. You are just counting, okay? So this will be 1, 2 alleles. 2, 4, 5, 6, 7, 8, and so. That's 50 alleles. So you're counting the number of uppercase D's, that's the dominant. And this is the recessive gene, lowercase d, that's 40. You are just counting, right? So this will be, for example, this will be 2 uppercase D's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Therefore, uppercase D's dominant allele or dominant gene is 10. All right, so then you calculate what's the p value. So how do you calculate the p value? P value is the frequency. Frequency means what? The number divided by the total population, right? So 10 over gene pool, the total, that's 50, and that's your frequency of D, and this is the frequency of lowercase d. Once you have these numbers, you can calculate P square, simple math, 2PQ and Q square. You're going to be using this for your lab, okay? Now, Hardy-Weinberg principle, remember, is a constant and said that the allele frequency in a gene pool means, remember, the total number of alleles, right, will remain constant as long as certain conditions are met. What are those? No mutation, no genetic drift, no gene flow, random mating, and no natural selection. All right? So obviously we know this, that all this possible. In theory, it is not possible. It's never achieved in a wild population. How will you stop? How will you prevent? How will you say that, okay, there should be only random mating, no non-random mating? All right. How will you prevent the immigration or emigration, movement of the animals from one population to another? That's not possible. So why do we study this? So why is it an important tool? Because why? Because if there's any violation of the conditions, then what's going to happen? The frequency will change in a predictable way. What did we say? P plus Q is always equals to 1, right? This is the allele frequency. Or better still, the genotypic frequency, the 2PQ plus Q squared is equals to 1. If you don't get 1, obviously one of the conditions are not being met, right? So I will not go over the entire table, but here obviously Hardy-Weinberg condition was random mating. Suppose there's no random mating. If there's no random mating, what will you see? You will see a change in the genotypic frequency. In this case, will p squared plus 2pq plus q squared equals to 1? No, it will not be. All right. So I'm more worried about solving Hardy-Weinberg equilibrium problems. So let's look at this. Here is a population of the black coat. Remember, the black coat is going to be recessive, and the white coat, which is going to be dominant. Okay, so here's a population, and remember, this is you can see the phenotype because you can count, right? You can see which ones are recessive, which ones are dominant. So it turns out that there are 4 recessive, and how many dominants are there? There are 16 dominants in here. Okay, so what do we need to do? Determine the percentage of pig population that is heterozygous for the white coat. So these ones that are here may be, remember, homozygous, right? Dominant, or what happens is heterozygous. So we have to calculate the heterozygous. Okay, so my first question is, what is my Q squared? So what is my genotypic frequency of the what? The recessive gene. So the recessive gene will be, what will it be? It will be 4 divided by 16 times 100, and that will be what? 25%, which is, which is 25%, and 25% can be written as 0.25. You agree? All right. So if you have Q square, then what is Q? Q will be square root of 0.25, which is equals to what? 0.5, right? This is simple math. Now, what do we know? P plus Q equals to 1. Yes, we agree? So, therefore, what happens is P will equals to 1 minus 0.5, which is equals to 0.5. That is P, right? So, once I have my P and Q, that's easy. Now, all I have to calculate is 2PQ. So, 2 times 0.5 times 0.5 is equals to what? 0.5, which is 50%. So 50% of the white colored coat pigs are heterozygous. Got it? All right, let's look at the second one. In a certain population, 1,000 fruit flies, total is 1,000, 640 have red eyes, and the remaining have sepia. The sepia is recessive, so this is recessive. So he says, how many individuals would you expect to be homozygous for the red color, which is homozygous for the red color? If this is recessive, so this problem is very much like the previous one, except our numbers are given. All right. So again, we start out with what is that? Q squared, which is equals to the recessive. Why? This is the homozygous recessive. I'm sure of this. So Q square will equals to what? 360, right? Where did I get 360? Because there's a total population of 1,000. 1,000 minus 640 will give you what? Will give me 360, which is the sepia, right? Remember, I said sepia is the recessive. So Q is equals to what? 360 divided by 1,000, which is equals to what? 0.36. Okay. So Q will equals to square root of 0.036, 0.36, which is equals to 0.6. All right. So if Q is 0.6, therefore P is what? Will be 1 minus Q, which is equals to 0.4. Got it? And therefore what has P square will equals to 0.4 times 0.4, which is equals to 0.16. So what is the homozygous? Homozygous. So here, remember, it will be 16%. 16%. 16%. That means out of 116. So out of 1,000 what? It will be 160 individuals will be homozygous dominant. All right. I think, this is the last problem. The Hardy-Weinberg equation is very useful for predicting percentage of human population that may be heterozygous carriers of the recessive allele for certain genetic disease, which is the phenylketonuria, PKU, which is a metabolic disorder. All right. So in the US, 1 out of how many? 10,000 are born. So what percentage of population are heterozygous carriers? May not express it, but are carriers. Always we start with Q square calculation. So Q square calculation is 1 over 10,000, which will be what? 0.0001, right? Yeah. So what is Q? Q will equals to square root of 0.0001, which is equals to 0.01. So if Q is that, P will what? Will it be 1 minus Q, which is equals to 0.99. Yes? So remember, we need to find out 2PQ, which are the carriers, are not expressing 2, 0.99. I'm talking 2 times 0.99 times 0.01, which is equals to what? 0.0198, which is equals to 1.98%. Correct? Approximately 2%. So 1.98% are my carriers. So hopefully you do understand Hardy-Weinberg, and if there are any questions or concerns, please stop by my office and ask me. All right. Thank you for giving me your time and attention.